Welcome to video 1 of topic 1.5. In topic 1.15, in topic 1.14, we talked about vertical asymptotes. We call those infinite limits, right? Because there isn't a limit value. It just goes to either positive or negative infinity. And a perfect example of this would be this statement right here. So this statement right here is telling me that this function, as x approaches 3, the function goes to positive infinity. So the first limit describes a vertical asymptote. And I know that because the outcome of taking this limit is positive or negative infinity, in this case, positive infinity. Well, that's different than the limit next to it. And so in this topic, we're going to talk about horizontal asymptotes. And that's what this second limit describes. And this is a horizontal asymptote. So they have some things in common, right? They both deal with some kind of infinity, but it's about where the infinity is. Is it in the outcome, in the output, what the limit is doing, or is it where I'm looking? I'm looking at the end behavior, which is as x approaches positive infinity or x approaches negative infinity, right? Like this part right here is what gives it away that we're looking at horizontal asymptote. Just like this part over here gives it away that we're looking at a vertical asymptote. So previously, I'm going to say, we were looking at infinite limits and how they're connected to vertical asymptotes. And so our goal in this series of videos is to talk about how limits at infinity are connected to horizontal asymptotes. Oh, that's terrible. Horizontal asymptotes. Again, the idea here is there's a difference between the green and the red. The green is telling me this is happening, or this is happening, or this, or this. But the red is telling me, oh, it's leveling off. If there is a value, right? Because we could have our end behavior go up at the ends. That means the limit as x approaches infinity of the function would equal itself infinity because it's just going up forever or down forever. So let's take a look at some of these. We're going to complete the table. So we're going to use the table as a guide to tell what's going on in this function. I went ahead and put in the function into my y1. I believe that's the exact function that we're given. I'm going to use the function notation. Remember, alpha trace produces all the y equations. I saved my equation in y1, and I'm going to input this x value. And when I do, this is the output that I get. I get 1/6. If you want, I suppose, we can convert that into a decimal and say that it's 0.166666. So I'm going to write that under 0.166, 0.166. And then you're going to fill in the table with the rest of the values, right? So let's look at I'm going to cheat and copy paste and change that 1 to a 0. So now I'm plugging in, substituting 10 into that formula that I saved in y1, which is the formula that's on your paper, and we get this. 298, there has to be a better way to do this here. I just haven't found it. 298 over 141. So 298 over 141. And that is, let's see. Let's change that to a decimal. 2.113. All right, so it's already changed, 2.113. All right, what happens when I substitute 100? So wait, why are we plugging in bigger and bigger numbers? Oh, because here my x is getting larger and larger and larger, and I want to see what's going on with this function. So we plug in 100. I'm going to go hopefully a little bit faster here. I'm just going to put a 0, and I'm going to get 100. Oh, 2.884. And I'm going to put it down here, 2.884. It didn't give me a fraction, right? And then the next one is 1,000, so I'm going to add another 0. 2.988. 2.988. You start to see a pattern. Are the y values outputs that we're getting, are they approaching a value, right? Because that's what a limit is. It's getting closer and closer to something. Is the next one 10,000? Because I'm about to put an extra 0 here, and I get 2.998. So if I were to stop there, what would happen as I keep putting bigger and bigger and bigger numbers into this function? What do you think it's approaching? This was 2.999. Where are all these numbers going? Or as I tell students, if you had to round it, what would it round to? Oh, it would round to 3. That means my limit is 3. So one of the things we're going to find out is whenever we deal with limits at infinity, because we're growing the x, and x is just getting bigger and bigger and bigger, really it's a race. It's a race to see who gets bigger faster. Does the numerator get bigger faster than the denominator? Or does the denominator get bigger faster than the numerator? Or do they get big at a relatively same rate? Because if you remember what we talked about at the beginning of the previous video, and I'll keep scrolling until I find it here, that's what this was about, right? If the denominator is getting faster, is getting bigger faster than the top, then my whole limit is going to go to 0. But if my numerator is getting bigger, infinitely bigger than the bottom, faster, then it's going to go to some kind of infinity. And if they're growing at the same rate, well, then it's going to be some kind of ratio of values. And so as I come back over here, here's what we know. We know that, and we talked about this when we talked about horizontal asymptotes, which was connected to end behavior, the idea that when I take the limit of the numerator, because I'm plugging in big values, really all I need to do is focus on the largest term, the biggest term with the biggest power in the numerator. And when I do the same thing with the denominator and I take the limit as x approaches infinity of this, I really just need to focus on, and I'm going to put an arrow not equal because they're not equal. I'm only going to focus on the denominator, the biggest term in the denominator. And then I see and compare how they're growing. Well, can I reduce that? I think I can. The x squares are going to go bye-bye because they're going to reduce out, and then I'm just left with 3/2. I'm claiming that 3/2 is the limit. As my x's get bigger, because the numerator and denominator both have the highest power of 2, they're going to grow at the same rate, and my answer is going to be the ratio between the top and the bottom. I think I call this a balanced fraction situation. Some people call it balanced as opposed to top heavy and bottom heavy, that conversation we had. So this is going to tell us that it's going to level off towards 3/2. So I guess the hint that Brian gives us here is when we're working with limits, that only with limits that are approaching infinity can I do this. Ignore the little terms and focus on the biggest magnitude in the numerator and denominator, what we call the leading term of the numerator and denominator, and compare those. Because when I compare those, either it's top heavy and it's going to go to some kind of infinity, it's bottom heavy, it's going to collapse down to 0, or in the case of this example, it's balanced and it's going to reduce down to a ratio of 3/2. In the next video, I'll graph this and I'll show you what it looks like to get started.